So this video is going to be the solution to the last worksheet we did in class, problem number 3. So not everyone got to this, and I wanted to go through this very carefully for you to help you understand how we're using the definition of the definite integral, and this is how you're going to use it on your written assignment that's due on Monday night. So in this problem, part A, we're supposed to use the definition of the definite integral to evaluate the definite integral from 0 to 2 of x squared minus x dx. And so in the previous problems on this worksheet, we had we'd gotten some approximations to this definite integral by taking some finite sums, getting areas of rectangles using right endpoints or left endpoints or midpoints. So those were just approximations, and so now we're going to actually find the definite integral. It's a limit. So we're going to take a limit of a finite sum from from 1 to n, but the limit is going to let n go to infinity, so the number of subintervals is going to go to infinity. So we have to set up a Riemann sum and then take the limit of it. So the definition is going to be this. The definition of the definite integral from 0 to 2 of x squared minus x dx. The definition is the limit as n approaches infinity of the sum from 1 to n of f of xi, which is xi squared minus xi times delta x, where xi could be any sample point from the subintervals, and delta x is the width of all the subintervals. And so in our definition, we're always going to use the right endpoint or the left endpoint just because it's an easier formula to use. And right now I'm not going to actually use the formula. I'm going to show you how to get it if you don't remember the formula. So first of all, we need to figure out what delta x is. We want to get everything in terms of i's and n's. That's our goal, not to have any more x's. And so the delta x is the width of all the subintervals. So we take the width of the big interval, 2 minus 0, and divide it by n, because there's n subintervals. So that's just 2 over n. So that's our delta x. Now, to get the right endpoints, let's just visualize where they are. So we've got this interval from 0 to 2. We've got a bunch of subintervals. So the right endpoints of these subintervals are x1, x2, x3. Those are the right endpoints. And they keep going. There's an xn minus 1, the second to the last one, and then the very last right endpoint is 2, and that's xn. Okay, so there's n right endpoints. So we want to get a little formula for the ith right endpoint, x sub I, and we want it to be in terms of i's and n's and nothing else, except maybe some numbers. So let's just look at how to get them. So the distance from 0 to the first right endpoint, x1, is just 2 over n, the width of the subinterval. And then the distance to the next one is 2 over n, and the distance to the next one is 2 over n. They're all spaced evenly apart. So we can write down what the right endpoints are, and maybe look for a pattern to see what the ith right endpoint would look like. So x1, we can see, is just 0 plus 2 over n, or just 2 over n. The next 2, we can tell by looking at it, is 0 plus 2 times 2 over n, or 2 times 2 over n. x3, similarly, is 0 plus 3 times 2 over n, or just 3 times 2 over n. So I'm not going to multiply those together. I'm just going to leave it like this so I can see what the pattern is. We can see that each of the xi's has a 2 over n in it, but the number in front changes, goes up by 1. So we can tell that the ith right endpoint is going to be 0 plus I times 2 over n, or just I times 2 over n. And just to make sure this works, let's see what the nth right endpoint would be. If this is the right pattern, the nth right endpoint would be n times 2 over n, which does work because it turns out to be 2. So we've got the right xi. So that's what we're going to use. We're going to use delta x, which is 2 over n, and xi, which is I times 2 over n, in our Riemann sum, our finite sum. So the Riemann sum, without the limit in front, is the sum from 1 to n of f of xi delta x, so xi squared minus xi times delta x. And using our delta x and our xi that we just found, we can write this as the sum from 1 to n of I times 2 over n squared minus I times 2 over n, all of that, times delta x, which is 2 over n. So this is our Riemann sum. And we have to take the limit of that as n goes to infinity. But it's not a closed form expression because of that sigma. But we're going to use some formulas to get it into a closed form expression. So we can use our limit laws or L'Hopital's rule, whatever we want to use to take the limit. So let's look at what the limit looks like. So the definite integral from 0 to 2 of x squared minus x dx is the limit as n approaches infinity of that Riemann sum that we just wrote down. So this is the Riemann sum that we found. Okay, so this is what we're going to work with and try to simplify so we can take the limit. So first of all, I'm going to square that I times 2 over n. So I have the limit as n approaches infinity of the finite sum of I squared times 4 over n squared minus I times 2 over n. All of that is still multiplied by 2 over n. So now I'm going to distribute that 2 over n into both of the terms. So it's I squared times 8 over n to the third minus I times 4 over n squared. So I've just distributed that 2 over n. Now my sum is a sum of a finite sum of a bunch of differences, right? I squared times 8 over n to the third minus I times 4 over n squared. So I can use one of the properties of finite sums to split it up into two finite sums. Still taking the limit, so I still have to write that. Limit as n approaches infinity. But now I'm breaking it up, and the first sum is just the sum from 1 to n of I squared times 8 over n to the third. And then I'm subtracting the sum from 1 to n of I times 4 over n squared. Okay, so now when I look at those individual sums, so let's look at the first sum, the sum from 1 to n of I squared times 8 over n to the third. The 8 over n to the third does not depend on I, so that doesn't change. It's in every term. So the first term in that sum is 1 squared times 8 over n to the third. The second term would be 2 squared times 8 over n to the third. The next one would be 3 squared times 8 over n to the third. So the 8 over n to the third doesn't change. It's in every term. So I can use the distributive property to pull it out in front of that sigma. And then the same thing in the second sum. And look at that one. It's the sum from 1 to n of I times 4 over n squared. So that 4 over n squared is not changing. It doesn't depend on I, so it's the same in every term of that finite sum. So that we can use the distributive property there to pull that out in front of the sigma as well. So now I'm going to rewrite it using the distributive property. So we still have n approaching infinity, but now we have 8 over n to the third times the finite sum from 1 to n of I squared minus 4 over n squared times the finite sum from 1 to n of I. Okay, so now we've got these two finite sums that should look familiar. There's two formulas that we can use on that handout. On the first front page of the handout are a bunch of properties. The second page of the handout is a theorem with three formulas. And so the first finite sum, the sum from 1 to n of I squared, that's the sum of the first n, the sum of the squares of the first n integers. The second sum is the sum of the first n integers. And so the first sum we have here is the second formula, and the second sum that we have here is the first formula, Gauss's formula. So let's use those two formulas to rewrite, and then we'll have two closed form expressions instead of finite sums that are written in terms of a sigma. So we've got the limit as n approaches infinity of 8 over n to the third times, now the sum of the squares of the first n integers is n times n plus 1 times 2n plus 1 all over 6. Then we're subtracting 4 over n squared times, and then we're going to use the first formula in that theorem, Gauss's formula. That one is n times n plus 1 over 2. And now we can simplify that a little bit, but we can take the limit right away using, the first limit laws that we learned, or using L'Hopital's rule, whatever you want to do. And when you do that, you're going to get 8 over 3 minus 2. So the first one is, the limit is 8/3, and the second one, the limit is 2, and that is simply 2/3. All right. So now, that's the definite integral. That is a real number. That's not an approximation. That's the answer. Okay, so let's look at the part B. So part B says interpret that integral as a difference of areas and draw a picture. So we have to draw a picture first before we can interpret it as a difference of areas. So we drew this parabola a couple of times, so we know what it looks like. It has a vertex at 1/2 comma negative 1/4. It looks about like that. And now we can shade in these two regions. So the first region, let's call that area A1. The area of that region is A1. That's a positive number. The area is always positive. And then the second region, we'll call that area A2. So the definite integral that we just computed, the integral from 0 to 2 of x squared minus x dx, can be interpreted as A2 minus A1. So the area of the region above the x-axis minus the area of the region below the x-axis. So areas are always positive, but when we're interpreting definite integrals, we can interpret it as the net area, we call it net area, of the region between the x-axis and the curve. So that could be partly below the curve, it could be partly above the curve, but we subtract the area below the curve from the area above the curve. In this case, we can see that the area of the region above the curve was greater than the area of the region below the curve. So our net area was positive. But in some cases, if the definite integral is negative, that's what it means is that the area of the region below the curve is greater than the area of the region above the curve. So when you subtract, you get something negative. All right, so this is similar to, but a little more difficult than the problem that you're going to do for your homework. All right, have a great weekend.